So we have a length of wire that is coming off of two poles. One pole is 15 feet and the other pole is 17 feet. And where the two wires meet at the ground, we're supposed to be minimizing the wire. So I'm trying to color this in with green just so you see what we're looking at. I am also told that, that's slightly more green, the width between the poles is 128 feet. So we're just going to arbitrarily say that this is x, and then we're going to say that this is 128 minus x. So this width, or this length, is going to be m, and this length is going to be n. And we're going to minimize the amount of wire used. So I do know that L, or the length of the wire, is going to be m plus n. So if I just use Pythagorean theorem on each triangle, then I'll know what m is and I'll know what n is, because I'll be looking at the hypotenuse of each triangle. So I have L equals, this one is going to be 15 squared plus x squared equals m squared. So the square root of both sides will tell me that m is going to be the square root of x squared plus 225. Okay. The next one is a little bit more complicated. So we have 17 squared plus 128 minus x squared is going to equal n squared. So I'm going to take the square root of both sides. So that gives me 289. And I've already got written out over here. Plus 128 minus x squared. So those are those two values. I'm going to go ahead and rewrite this one out, just so it's a little bit easier to take a derivative with. Okay, so I have L equals, we'll do x squared plus 225 to the 1/2 power, plus, and then this is going to turn into x squared minus 256x, plus 16,673. Raised to the 1/2 power. So I just FOILed out the 128 minus x squared, because that's supposed to be squared. Oops. I FOILed that out, and then I combine the like terms with the 289, and then this is what I've got. So now it's ready for me to take a derivative, so I'm going to start writing this over here just so I don't get cramped. So this derivative is going to be 1/2 of x squared plus 225 to the negative 1/2 times 2x. Okay, so that's this derivative. This derivative is going to be plus 1/2 times x squared minus 256x plus 16,673 to the negative 1/2 times the derivative of the inside, which is 2x minus 256. Okay, so where can I go from there? Well, I'm going to clean up this first one a little bit. So this 1/2 and this 2 reduce. So that leaves me with an x over the square root of x squared plus 225. And then we've got plus. This 1/2 is going to reduce with both of these, and it's going to become an x minus 128. So I'll have x minus 128 over the square root of x squared minus 256x plus 16,673. And we're setting that equal to 0. So this is a nightmare to work through algebraically. So what we're going to do is we're going to go over to Desmos, which is an online graphing calculator. and we're going to put this as an argument into what we're trying to graph. So you can do it on your TI-84 or your TI-83, but it's not going to be near as pretty or near as easy to do. So with the Desmos online graphing calculator, you will be able to trace, just by, even if you've got a touch screen, use your finger, trace the graph until you find where it hits the x-axis. And when you do that with this particular setup, you find out that x is 60. So how far away do we want this to be? This length is 60 and this length is 68. And that is it for that problem. All right, so I'm given that there's a 9-foot wall, or a 9-foot pole, okay, that's 30 feet away from a building over here. So I can't remember if this is a pole or a wall, whichever. Okay, so this is going to be very, very similar to the curtain rod problem that we did, but we're still going to go ahead and set it up. So I've got that this is theta, and I've got that this is theta. So I'm going to go ahead and do this triangle right here. And I'm going to decide that this is going to be x. And I've got this triangle right here. And I'm going to decide that this hypotenuse is going to be y. So the length of the cable is going to be x plus y. So the hypotenuse of the triangle from the wall to the building, and the hypotenuse from the ground to the wall, those added together are going to give us our values. So remember that this length right here is also 30. So what I'm looking at is this triangle, and I'm looking at this triangle. So what do I know about the triangle with the x? Well, I do know that this is adjacent over hypotenuse. So adjacent over hypotenuse is cosine. So that is 30 over x. So I can rewrite that as x times the cosine of theta is 30. And I can rewrite that as 30. I'm going to divide both sides by cosine. So that gives me x equals 30 secant theta. So x equals 30 secant theta. Okay. So what did I do? I set up my ratio. I multiplied both sides by x, and then I divided both sides by cosine. So 1 over cosine is the same thing as secant. So we're going to do that exact same process, and we're going to do it with the other triangle. So what do we have with this one? We know that this is opposite over hypotenuse. So I have the sine of theta is going to be opposite over hypotenuse. So I'm going to go ahead and multiply both sides by y. And then I'm going to divide both sides by sine. So that gives me 9 cosecant theta. So 1 over sine is 9 cosecant theta. So what we have now is x plus y is going to be the same thing as x, which is 30 secant theta, plus y, which is 9 cosecant theta. So this is what I am maximizing or minimizing right here. So now I'm ready to go ahead and go in and start taking derivatives. So I'm just going to rewrite this down here just to be a little bit more clear. So L in terms of theta is going to be 30 secant theta plus 9 cosecant theta. So now the derivative of that, well, what's the derivative of secant? The derivative of secant is secant tangent. So I have 30 secant tangent plus the derivative of cosecant is negative cosecant cotangent. And now I've got that cleaned up. So I'm going to go ahead and bring this negative out front. So I have 30 secant theta tangent theta minus 9 cosecant theta cotangent theta is 0. And from here, I can go ahead and add 9 cosecant cotangent to both sides. So just to clean this up just a little bit, we've got add this to both sides. Okay, that's cosecant. So from here, I now have 30 secant theta tangent theta equals 9 cosecant theta cotangent theta. Well, I can rewrite secant as 1 over cosine. And tangent is sine over cosine. That's going to equal cosecant, which is 1 over sine. And cotangent is cosine over sine. So are we happy so far? This gives me 30 times sine theta over cosine squared theta equals 9 times cosine theta over sine squared theta. So I've got to flip my page. But I'm going to go ahead and divide both sides by 30. I'm going to multiply both sides by sine squared. So this is going to be divided by 30, divided by 30. So I'll write it a little bit messy over here, and then I'll clean it up on the next page. So that gives me sine squared. So if I cross multiply here, or multiply both sides by sine squared theta, sine squared theta, that's going to give me 9 over 30 equals sine cubed theta over cosine cubed theta. So I'm going to write that again. So all I did was I kind of ignored these. Okay, where'd this go? I kind of ignored these and I cross multiplied. But what I really did technically is I multiplied both sides by sine squared and I divided both sides by cosine. So that got the trig identities on the left and that got my ratio on the right. So looking at this and writing it a little bit more clearer, I have the sine cubed of theta over cosine cubed theta equals 9 over 30. So this is the same thing as tangent cubed theta equals 9 over 30. And now I can take a cubed root of both sides and find out that the tangent of theta is going to be, I've lost my calculator. So the tangent of theta, or sorry, let's not do that yet. The cubed root of 9/30, so 9 divided by 30 raised to the 1/3 power gives me 0.66943. And then 295. Okay. So the arctangent of that, because I want to know what theta is. So the arctangent of that, I'm going to take the arctan of both sides. So that'll give me theta equals the arctangent of 0.66943295. So when I take the arctangent of this, after I make sure I am in radians, so hang on, I don't remember how to do this. Degrees, radians, okay? So the arctangent of this, 0.6694325, is going to be 0.5899. 15,278. Okay, that's what theta is. Well, now we want to go backwards because we happen to know what the length of our sides are in terms of trig functions. So L theta was 30 secant theta plus 9 cosecant theta. So that's going to be 30 times the secant of 0.5899 plus 9 times the cosecant of 0.5899. So remember, that's just 1 over cosine, and this is 1 over sine. So this is going to give me about 36.1, and this is going to give me about 16.2. So I find out that the length of the cable that it's going to need to reach this thing is 52.3 feet. Okay? All right, there's a lifeguard at point A who is trying to reach a drowning person at the exact opposite side of a circular pool at point C. He swims at a rate of 1.49 meters per second. He runs at a rate of 2.98 meters per second. And the width of the pool is 54 meters. Okay, so we've got these triangles set up. Sorry. Anyway, so this triangle in the middle here, or coming off this side, has an angle measure of theta. And it goes up to B and down to D and back over to A. So triangle ABD has a sine of theta of BD over AB. So opposite over hypotenuse. Okay? And I intentionally drew this as a vertical drop so that it would be a right triangle so that I could use trig functions. So what we just figured out is that the larger triangle has a sine ratio of BD over AB. Okay? We also know that this smaller triangle in here, we're just supposed to remember from geometry that if this angle and this angle subtend this same value here, then this must be double whatever that is. Okay? So this central angle will be double whatever that is if they subtend the same vertical, or the same angle. The same line segment. Good grief. Okay. So that means that triangle BOD, which is triangle BOD right here, is going to equal sine 2 theta is BD over the radius. So the radius is OB. So instead of me writing it as OB, or BO, I'm going to write it as the radius because it's the same thing as BO or OB. Okay, if I multiply both sides by R, then I'll get the sine of 2 theta is BD. So that is where we are at this point of the game. So we have, if sine theta equals BD over AB, okay, then AB equals sine theta, then AB times the sine of theta will equal BD. So AB times the sine of theta, because I multiplied both sides by the segment AB, which means I now have some additional information. So AB, because I know what sine theta is, okay, so what I'm going to have here is AB equals R sine 2 theta. Oops, I forgot my 2. R sine 2 theta over sine theta. Okay. Which gives me, if I remember the fact that a double angle identity for sine is the same thing as 2 sine theta cosine theta. So this sine 2 theta is going to turn into 2 times r times sine theta cosine theta all over sine theta. So the 2 sine theta cosine theta is the same thing as sine 2 theta. And the r just came along for the ride. Well, now my sines reduce out, so I'm left with AB is 2r cosine theta. Okay, so that's what I've got so far. So arc BC, this goes back to just a ton of geometry. So arc BC, which is this part of the circle, which is not drawn very circle-y. Okay, so arc BC, by definition, so here's an arc, is going to be 2 pi r, which is the circumference of a circle, times 2 theta over 2 pi, which gives me 2r theta. So that is how far that is. Okay? So we've got the circumference, we've got the angle measure of 2 theta, subtending that arc right there of BC. And then we're going to divide it by 2 pi because that's the distance around the circle. So we know a ton of information. So at this point in the game, what do we have? We've got t of theta, because we're looking for time, is going to be segment AB, which he should swim in 1.49, plus arc BC, which he should run at 2.98. Okay, so he's going to swim across at 1.49 miles an hour, or meters per second, and then he's going to have this arc length right here of 2.98 meters per second. Okay, so he'll run this arc length at 2.98. Now, it is important that we come back here and recognize what our domain is. Our domain is going to be from 0 to pi over 2. And why is that? Because he can either swim the whole way, which would be an angle measure of 0, or he can run the whole way, which means he'll never, ever get in the pool. And that's going to be an angle measure of pi over 2. So we're not going to go into quadrant 2 or quadrant 3 or quadrant 4. We're just going to say he can either go straight across, which means theta would be 0, okay? Or he can go and run the whole way around, which would be theta equals pi over 2. So, where am I at? All right, so knowing what we know about AB, we have AB is the same thing as 2r cosine theta over how fast he swims, okay? And then plus 2r theta over 2.98, which is going to be how fast he runs. So remember that my radius is 27. The distance across, or the diameter to the pool, is 54. So my radius must be 27. So now we can substitute in our r value. So t of theta is going to be 2 times 27 times the cosine of theta over 1.49 plus 2 times 27 times theta over 2.98. So that is what I have so far. And when I take a derivative, actually let's clean this up just a little bit first. This is going to give me 54 over 1.49. And this is going to give me 54 theta over 2.98. All right, so I would like to know what to do now. I now have my cleaned up equation that I need in order to find how far should he run, how far should he walk. What am I going to do with this? I'm going to take a derivative. So the derivative of this is going to be the derivative of cosine is negative sine. So I have negative 54 sine theta over 1.49. So the 54 and the 1.49 are just coming along for the ride. And then what's the derivative of theta? It's just 1. So I have 54 over 2.98. And I set that equal to 0. Okay? Set that equal to 0. So I am going to add 54 sine theta to both sides over 1.49. Which gives me 54 sine theta over 1.49 equals 54 over 2.98. Okay. Hold, please. Sorry, I had to let my dog out. Okay. So this is what we've got so far. I'm going to divide both sides by 54. So that gives me sine theta over 1.49 equals 1 over 2.98. And now I can cross multiply. So I've got 2.98 times the sine of theta equals 1.49. And I'm going to divide both sides by 2.98. So I find out that the sine of theta needs to be 1/2. So in our case, theta, where does sine equal 1/2? It equals it within our domain at pi over 6. So from here, we want to find an absolute min from 0 to pi over 2. So we are given 0, we're given pi over 6, and we're given pi over 2, and I want the lowest value. And remember, when you're doing absolute maxes and mins, substitute these values back into your original equation. So my original equation would be, where's my cleaned up one? Right here. So T of theta is going to be this equation. So we're going to substitute these values in, and I've already done it. I've already written it down. I get 36.242. I get 31.386. And I get 0 at pi over 2. So which is the minimum value? Your minimum value is at pi over 2. So what does that mean? That means that the man should run the whole way. So the way the question is phrased is how far or at what angle should he swim? Well, he should swim at pi over 2, which means he's out of the pool. Okay, so he must be running if he swims at pi over 2.